Hi folks, Dan from D&N Custom Creations. Today I want to talk about demystifying the Langmuir initial height sensing process. If you've been like me, you've been using the pierce height and the cut height. You set that in your post processor and the Langmuir has done a great job. But there are some conditions in which you could be resulting in your heights, what you think is the height that you set, actually being different than what you set. And it's almost entirely due to backlash in the Z-axis system and spring back, especially the values that you've set. So today I want to talk about just the initial height sensing system. The torch height control system, I'm going to leave to a future video. We'll do that following this, but we'll concentrate. Now, they're very related, but you could run your table without torch height control. There's a whole bunch of people doing it. In fact, the people that don't have the Pro torch table, that's all they have. So I think there is you can now get a torch height control system for that table, but regardless, you can run your table without that. The only real issue comes with you've got things that have a lot of bow in what you're cutting, then that's where the torch height control really comes into play. So they're very related, but we're going to concentrate in this video just on the initial height sensing system. So here's what I want to cover in this video. I'm going to define what torch Z motion that I'm going to attribute to the initial height sensing process. I mean, in reality, when you look at the definition of initial height sense, you could almost imply that it's only the torch coming down and actually sensing the top of that plate and the IHS is done. But I believe it's more than that, and I'll define what I believe that is. We're going to look at the switch that's used to indicate that the torch has contacted the top of the material being cut and how that works. We're going to demonstrate plate spring back, which in a conclusion, in the end, I believe is the major factor in when you set a value for pierce and cut height. In reality, it's going to be different than that, and it's all due to that spring back command. We'll do a short review of the G-code command used by the initial height sensor, and we're going to observe and measure that Z motion as that process executes. And then finally, we'll discuss why those pierce and cut heights by the user don't match what actually occurs. And it's, again, I believe it's entirely due to the spring back and backlash corrections that are integrated into the it says HIS process. There's your spell checker. Keeps changing IHS to HIS. Anyway, so that's what I'm going to try and cover in this video. So here's where I define what I am attributing to the IHS process. And again, I already mentioned that in reality, it's an IHS may only be when it finds the surface of that table or whatever you're cutting. But I'm going to include the IHS is the downward torch motion until that torch contacts top of the plate, compensation for the plate spring back and backlash in the Z-axis, then moving the torch to the pierce height, moving the torch to the cut height, and then after the cut loop is done, moving the torch to the retract position after that's completed. And both IHS and the torch height control does this on every cut loop. So if you've got something that's, an intricate pattern, has to cut out, 50 different holes or patterns or whatever, every one of those 50 cut paths, it's performing the initial height sense and the torch height control if you've enabled torch height control and you have it on your machine. But right now we're going to concentrate on just the initial height sense. A key part of the initial height sensing is obviously the torch contact switch, because when the torch comes down and contacts the plate, the way that it determines that it has made contact is that it opens the contact switch. But it's more than just driving it down until it touches the plate. there actually has to be overcome the weight of the torch and the torch holder and the torch attachment to the Z-axis carriage, etc. Has to overcome that weight before it actually finally opens the switch, and we're going to demonstrate that. So there it says the weight of the torch applies downward force to the plate. Only once that weight has been matched by the plate will the contact switch open. And then plate spring back plays a significant role in how far that torch continues to travel downward even after contact has been made before that contact switch opens. And I'm gonna show you that in a small demonstration. We're going to be talking about the contact switch that the IHS uses in order to determine that the torch has actually made contact with the plate. So I want to narrow in on where that location is. You know, here is obviously the Z-axis, and right in here, if I can get you in close, you see this little copper plate. It is insulated from being able to make contact with the metal parts by some plastic bushings, but it has a tab, if I can point it out, right here, if I can get you in real close, that contacts a screw that's on top of this nut that follows the lead screw. I'm going to lift up on the torch and you'll see that that copper plate, when it touches that screw, that's the switch has made contact. When it's lifted up, then it breaks contact. If I can get it over there a little bit closer. So there it's lost contact, contact has been broken. Their contact has been made. And so that's basically the extent of that switch. There is a spring, notice underneath, that provides some spring tension for the torch, but in reality, it's the weight of that torch that is pushing down on that whole carriage assembly that's riding up and down on that Z-axis. It's the weight of the torch and the carrier, the torch holder, as well as this mechanism here. All of that together provides the weight, and just from gravity, obviously, then pulls down on that so that it's resting against that screw. So that little lead screw nut, this little black nut right here that rides along the lead screw, as the lead screw turns, that nut goes up and down. And since it's contacting this brass piece or copper piece, whatever it is, follows that. So that as the little lead screw nut goes up and down, it makes the torch go up and down. So it's basically following that. And if the torch were to stop and that lead screw continue to turn, especially going down, then that switch will open. And that's the way that works. So I mentioned that the weight of the torch and a carriage assembly, etc., is what drives that torch down, and that torch has to stop with the lead screw nut continuing to move down in order to make that switch open up. So what's the impact of the weight of that torch? Well, it's the weight of that torch and carriage assembly, etc., that results in this thing that we call spring back. And we'll take a look at that. I'm going to lower the torch slowly. We're going to look at the weight, and I'm going to have to do this kind of by eye, but I'm going to notice when the switch opens, when that copper tab moves away from that head of that screw. We're going to look and see what's the actual weight that's pushing down on that plate at that time. So let's see, let's get this thing going. I'm looking in to see when that copper plate has moved away. There it is. Okay, so we can take a look at that now and see that we're looking at about 3 pounds 1 ounces of force that's pushing down on that plate before the switch actually opens. So it's not the instant of contact. If the plate, if the plate that it's pushing on can flex a little bit, it's going to flex it until the resistance is enough to meet that 3.1, or actually 3 pounds 1 ounce. It's not 0.1 pounds, but it's 3 pounds 1 ounce. Once it overcomes that amount of force and can actually then open that switch, that's what you're seeing. So that's what's causing that spring back. And I'm going to show you that in a little easy demonstration to give you a little better idea what's going on. Hold on. Okay, let's demonstrate this spring back. We're going to assume that this is the weight of the torch and carriage assembly, etc. We're going to assume that this connection right here is the switch. This is the copper plate, and this is the head of that screw. So as I lower something down, it gets to the point now where the weight of the torch is fully supported. The lead screw continues to drive the lead screw nut down, and you've broken contact here at the switch. So now let's think this is the plate that it's sensing. Well, you can see that as I lower this weight down onto that piece of material, it continues to move. I still am making connection with that above, so representing the contact switch, until some point in time it's supporting all the weight of that, and now I've now broken contact. Well, that distance that it has moved, it is contacted right there, but it is not broken a switch until that plate that it's sitting on has moved far enough to provide complete support of that, and then now breaks the contact. So that amount of motion is what we call spring back. That's obviously exaggerated, hopefully over some of the plates we're cutting, but that gives you a visual demonstration. And we're going to actually look now, we're going to put a thin piece of plate on the table and see how much spring back occurs before it stops. Okay, we did a little demonstration of plate spring back assuming the weight of the torch, etc. We're going to actually see it now in operation. So I put a little code in there that is going to drive the torch down to basically looking for the top surface of that plate, and it's going to continue to move until that switch opens. And with the dial indicator here, we'll see how much this little piece of material moves before the switch finally opens. So let's get it to run here. And it's going to sit there for about 10-15 seconds, and then it's going to go back to its original position. So it moved about 103 thousandths down before the switch finally opened. Well, that 103 thousandths represents the spring back, or the spring of that plate. So now when it goes back to its zero position, well, that plate obviously springs back, and you see it's gone back to its zero position. Well, that motion is what we'll refer to as a plate spring back. Obviously, for thin material that's bowed, you're going to have a lot. If the plate is a little different now, let's assume now it's this heavy plate. This is a 1/2-inch plate. And I'll again kind of set it up so that we're zeroed out. I'll move the torch over a little bit. And now let's see how much motion there is before that torch opens the switch. So here it's driving down. This is the same program. As soon as the switch opens, it's going to stop. Well, there it stopped. Would you see moved maybe 1/1000th or 2/1000ths of an inch. So you can see, depending on what you're cutting, you might have a lot of spring back, you might have almost zero spring back. So that's where that spring back command or function in the initial height sensing system or the process that's where that becomes an important quantity. And we're going to look at that a little bit later. Now we're going to actually exercise this torch and have it do all of its pieces of what I defined as the initial height sensing process. But you need to understand enough of the G code to know a little bit about what's going on. I'm not a G code expert, and I'm not going to spend a whole lot of time on this, just the fundamentals so that you know what's happening. And the G code, if you were to pull open one of your G code files, one of your cut files, and look at what's there, you're going to see these in every cut loop. You're going to see these commands. The first part is it starts out and it says G38.2. That's a probe command, and that's going to move the torch toward the plate. Now that command says stop on contact. In reality, what Langmuir has done is it's going to stop as soon as that switch opens, because that's going to indicate to this probe command that it has made contact. And that code will probably look like something like G38.2 Z5 -5 F100. Essentially what that means is the torch is going to move down in a Z direction downward at a speed of 100 inches per minute for a maximum distance of -5 inches, or until contact is made. Well, obviously you want contact to be made before it goes -5 inches, but that's what's in there as the default. The next command is a G38.4 that moves that probe away until there's a loss of contact. And what Langmuir has done is it starts moving that torch back up. The lead screw starts to turn, that the little screw that's on that lead screw nut begins to move, and as soon as it makes contact with that brass plate again, then the switch is closed, and that indicates that it has lost contact. In our particular case, that says I've lost contact with the plate. Well, the code really looks like G38.4 Z0.5 F20, which means that it's moving upward at only 20 inches per minute, and it's going to go a maximum of ½ an inch, or until that switch again makes contact. Well, in reality, it moves very little, and we'll see that when we actually exercise it. A G92 command is an offset. It basically says, I don't care where you're at right now, and we're talking here about the Z-axis system in particular. It says, I don't care where you're at right now. Wherever you're at, I want you to assume that's 0. And so now that it's 0, if I tell you to move 15 thousandths of an inch, it's going to move 15 thousandths of an inch from that position. Okay, so G0, rapid move. This just moves in a rapid motion. So G0, Z.1 or Z1.0, that's you'll see that in your code, especially when it goes to the retract. So after the cut is made and the torch goes up, about to an inch, that's your retract position, so that it can move to the next cut, hopefully without hitting something in the process. So when you're cutting stuff and your piece of metal kind of tips up, hoping that 1 inch, that it will clear some of those. Sometimes it does, sometimes it doesn't. M3 is just a torch fire command. M5 turns that torch off. And then finally G4 is a dwell command. And typically this is what you'll see when you have your pierce delay. You're going to see a G4 command. So in this particular case, a G4 P0.7, it pauses the motion for 0.7 seconds. It doesn't change the effect on the torch, so that's why the torch can fire, and then it can sit there for that G4 0.7 command, and then starts its actual cut path. So G4 is the dwell. We're going to use the G4. I'm going to actually insert pauses in between each of the IHS steps, so we'll get a chance to look at what's happened and do a little measurement before it moves to its next position. Before we get to our G-code example, I want to show you on the Hypertherm and using Fusion 360 what the post-process panel looks like that has the user input. Actually, it doesn't matter if it's Hypertherm. This is a Fusion 360 post-process. This is where you enter the information. And there are a couple of things like in bold there, cut height. I've chosen here to use a cut height of 0.06. There's the IHS springback command. I've chosen to use a 0.02, so 20 thousandths of an inch. It's going to assume that the plate's going to spring back 20 thousandths of an inch. That's basically what that command is saying. I've got IHS is turned on. Yes, well, we want to exercise that, so it better be. Pierce delay, I've got as a 0.06 or 0.6. Actually, that should be, yes, 0.6, I'm sorry, 0.6 seconds. So you remember in our systems, if the cut charts actually had, say, 0.3 as your pierce delay, we have to add a little bit because there's a little delay in the Langmuir's turning the torch on compared to what the Hypertherm cut chart's saying. So in this particular case, the cut was probably a 0.3. I added 0.3 seconds to that. That's why the pierce delay is 0.6 seconds. The pierce height there, 150 thousandths. That's comes out again out of the cut chart. And there's the retract of 1 inch. And we'll see that as we exercise this process. The rest of that information below that is probably not pertinent to what we're trying to do here. Okay. Let's start actually looking at a G-code example, and this is going to be based on that user input that you saw in that processor. Here was our G92 Z0. That basically says that the current Z heights set that to be 0. So wherever it is the start of this cut, assume that's the Z0. There's your G38 where you're moving your torch down at 100 inches per minute. And for our case, it's when that contact switch opens, it'll stop. Here's the G38.4, moves back up, and it's at 20 inches per second, per minute, sorry, until the contact switch closes. Now, wherever that winds up closing, now you get another G92. Says, okay, now where you're at, set that to be my new 0. And so if I tell you to move from there, that's going to be 0. So the next thing is a move. Moves 40 thousandths in the upward direction. That's a plus 0.04. And that's to handle the spring back and backlash. Now, we'll notice that in the user post-processor, I had that value spring back set to 0.02. It turns out that Langmuir, in their post-processing code, adds 0.02 to whatever value you put in there. So if you were to put a 0.05 in there, it's going to wind up here being a 0.07. If you put 0 in there, it's going to wind up being a 0.02. And we'll talk about the impact of that, especially for plates that don't move at all, that don't have any spring back. Now, once that is done, it is moved up the 0.04. It says, okay, that's your new Z0. So now again, wherever you're at, how far you are from that plate, after I've done all this 0.04 motion and taken out backlash and everything else, that's now assumed that that's 0. From there now, the G0 move 150,000 to 150 thousandths of an inch. So from that move, it's going to move, it could turn the lead screw until it has moved to a position of 150 thousandths based on that Z0. Fires the torch, pauses for 0.6 seconds for the pierce delay, then moves immediately to the 0.06 position. So it's going from 150 thousandths to the 0.06 position above the table. And that's your cut height. After it's done doing its cut, I don't have any motion here. There would be in a normal G file, but once it's done, turns the torch off, and then retracts the torch to 1 inch high above the position. Okay. So I've taken that G-code example and I've modified it to include pauses and a couple other things. I've reduced the speed. Remember, this one was 100 and this one was 20. I've reduced the speed down to 10 so we can see the motion. Every place where you see the circle here, I've inserted a pause of 10 seconds. And then I have put parentheses around the torch fire on and the torch fire off. The parentheses just basically when it's executing the code, it ignores anything that's got that around it. Okay, so that's the one that we're actually going to use and watch and exercise the IHS. Okay, we're going to exercise that little snippet of code that we had discussed where I'd modified and put pauses inside of that loop. And that loop really consists of everything that I believe is part of the IHS system. We got a dial indicator this is attached to the torch, so we'll see as the torch moves up and down, we'll get the dial indicator. I've got some gauge blocks. There's a 1 inch gauge block, so theoretically where it's sitting right now should be 1 inch. You see it's not. There's 150 thousandths. That's the pierce height that we've selected in the user input. And then I've got some feeler gauges that will check that 60 thousandths, cut height, etc. So I'm going to exercise this, and we're going to come down. This is a 1/2 inch plate, so there should be no plate deflection to speak of, maybe a thousandth or two just because it's sitting on some slats that can move. But in general, it should not move at all. All right, I'm going to get this thing started. There it is moving down. Once the switch opens, it'll sense that it has gone down. It's moved to about 925 thousandths, maybe a little more than that. Okay, it'll sit there for the 10 seconds, and then it's going to move. The next command is to move up until that torch makes. And when you watch this, you'll see that you don't see really much motion at all. In fact, I'm not sure you'll see any. Now there's the 40 thousandths that's been added. Now that's supposed to be 40 thousandths, but in reality, when I measure it, it's not 40 thousandths, it's 27 thousandths. So where did that loss go? Here's the 150 thousandths, supposed to be 150 thousandths, but again, that 150 thousandths is off by about 27 thousandths. Now it's going to go down to the 60 thousandths. In reality, when I measure that and get a good reading, that's actually 87 thousandths. Now it'll finally go up to its 1 inch retract value, which there's a 1 inch gauge block, and you see we have that same 27 thousandths difference. So what's caused that? We're going to look at a little diagram and see where that came from. Okay, here's my attempt to get a diagram of what we just witnessed with that torch throughout its IHS process. So the first step we saw, this G38.2 command drove the torch down until it contacted the plate and the switch opened. And then remember we set a pause there, etc. The next command moves it back up until it contacts that switch, makes contact again, closes, and then it sets that position as the new Z0. The next is this backlash and spring back command. And again, talked about that 0.02 was added in the post-processor because when I set the post-processor setting, I did a cut height of 0.06, pierce height of 150 thousandths, and a spring back of 0.02. Well, when it actually wrote out the G-code, that became a 0.04. So the lead screw turns to lift that lead screw nut. That should be 0.04. But in reality, it only moved 0.027. And the difference being is, as that lead screw turned, there was not enough motion of lifting the torch until you took out all the backlash. That means that in my particular system, I got 13 thousandths inch backlash. I would assume that, if you continue to use this thing over some period of time, that little plastic lead screw nut wears, because it'll wear before the lead screw does. And as it wears, that 13 thousandths backlash might grow who knows how far. But anyway, it tried to move up 0.04. It actually only moved up 0.027. But then it sets that new Z0 there. So it's sitting 27 thousandths above the plate, but it's saying that is 0 in reference to that plate. And so now when it says, okay, and go to 150 thousandths for my pierce height, well, when you measure it, it actually went to 177 thousandths. And that's because it had this 27 thousandths already there when it set the 0. So that's why it said go to 15 thousandths, but actually it was already sitting at 27 thousandths. So you wind up with 177 thousandths above it. The next thing is it dropped down to the cut height. But again, because of that 27 thousandths that came over here, it's really, in reality, it's sitting at 87 thousandths above the plate. And then when it finally retracts to 1 inch, when you measure with the gauge, that's actually 1 inch and 27 thousandths. So that's where the spring back and backlash come in. It can artificially add something to your plate Z0, or the surface of the plate, in order to compensate for spring back and backlash. Well, let's say that in my G code, I said, okay, I'm going to set my spring back to 0. And now we find out when it prints outputs the G code, there's the 0.02 that it automatically adds. And so what you basically see is the same thing, although again now it only went to 0.02. So as it moved up, remember the backlash is 13 thousandths. So in reality, it stops at 7 thousandths above the plate. That's an error. That should be 7 thousandths above the plate. And that error looks like I progressed through there. I did a lousy job of cut and paste. But in reality, when it goes to its pierce height, in reality, when you measure it, it's 157 thousandths instead of 150 thousandths. Ignore that error right there, and same in this particular case. And so when it gets to the cut height now, because over here we only moved up in reality 7 thousandths after we took out the backlash, I'm now sitting at 67 thousandths instead of 60, which is what my intended cut height was supposed to be. So that's it shows you that the value you put in here for spring back can be pretty important for your pierce and your cut height. If you use a large spring back value and your plate doesn't spring back, well, you can be significantly above your cut and pierce height that you think you have. And so this is one area that I think would be important for us to understand. We can, if we're getting lousy cut quality, maybe a lot of dross or etc., we might want to make sure that the actual torch height is what we intend it to be. I want to end this video with a little sequence of this in real time. So I've got the torch down and up heights, etc., to their default position. Goes down at 100 inches per minute, going up at 20 inches per minute, and I'm cycling it through 5 times. Now there's still a 1 second pause in between, otherwise you wouldn't see much of anything. But just again, kind of demonstrate so you get a feel for what's going on. Okay, I'm going to do that one more time, but I want to bring you over so you can see the lead screw switch. All right, I'll try and hold this as steady as I can. Let's start this thing over. See, there's the opening of the switch. There's brought it back up till it made contact. The opening of the switch brought it back up till it contacted again. Well, if you stuck with me through this entire discussion of the initial height sensor, you probably know more about IHS than 95% of the folks that use the Langmuir tables. I'd like to talk a little bit about what we do next. As I mentioned earlier at the beginning, the initial height sensor and the torch height control are very well related. And so now that we've done the IHS, the next video I'd like to do will discuss the torch height control. And in that, and actually what kind of led me down this path was I was wanting to cut some things, and I had contacted tech support, Langmuir's tech support, to ask them the best process. And their response to me said that if you're using torch height control, that they recommend that you go into the cut charts, and where they've provided you a cut voltage, use that as opposed to the pierce height and the cut height. Actually, the cut height is probably more important. So that's what started me down this path to understand IHS and a torch height control. The video would have been real long if I tried to include torch height control as well, so I didn't do it. I'd like to conclude by saying I think we've learned some things about the spring back and how that spring back parameter that you put into your post processor, depending on what you're cutting, if it's cutting that does have a lot of spring back, you know, then parameter might be one thing. If it's got zero spring back, then you might need to take into account that the post processor already adds 20 thousandths to your number that you put in there. And perhaps what I'll do in another video is play around with those parameters and then look at actually cut quality for a couple of things. If I can get a chance to do that. And finally, you know, I've been real happy using the pierce height and the cut height parameters and letting you know, the system do its thing. And in general, it's done a pretty good job. You know, I think the Langmuir folks have done a great job coming up with a system that works great. But I also believe that there are probably some times when we can tweak our parameters and do even a little bit better job than just depending, you know, as a black box on particularly cut height. In that torch height control, we'll also talk about Langmuir's suggestion, recommendation. If you're going to cut something that you don't have, you know, real good parameter in the cut chart, like for instance, if I cut 11 gauge, well, there's no 11 gauge in some of those cut parameters. It goes from 10, you know, up to the next, I guess, 12. And so their recommendation is to do a cut and monitor the voltage, and then set that. You let that become your nominal voltage that you set when you go into the settings on the torch height control. And we'll talk about that. We'll talk about how you actually do that. Okay, so thanks for spending the time. I know it was a long video, but I appreciate it. And this is DNN Custom Creations.